So today we are going to talk about stationary time series. Now, what we mean by stationarity, forget about time series data or forget about statistics or machine learning. By the very word stationarity means it is somewhere stuck. It is at a particular position, or it is a particular position in the space and time, and it is not deviating from that position. Okay, then we can say it's a stationary. So there is a concept called geostationary satellite. What is it means? Means the particular satellite is being positioned in the space at a particular point in space and time, so that with the rotation of the earth it will move also accordingly, right? So that means it is stuck in somewhere. The same concept we are bringing in the time series. The concept of stationarity also comes under something called regularity. Means if we don't mention, and whenever we will say that all the regular conditions, by saying that we mean that basically my time series is stationary. Okay, what does it mean? Let us try to understand what stationarity mean in context of time series. If you have a collection of time series values xt1, xt2 to xtk, okay. Now last time we studied the joint probability distribution. Now you shift that time series by a constant time h. So from t1 to t1 plus h, t2 to t2 plus h, t3 to t3 plus h. The probability distribution of this guys, joint probability distribution of these guys and joint probability distribution of these guys are identical. There no change. This is precisely what they mean by stationarity in time series. So imagine you have a particular time point, you have a bunch of data. It has certain distribution. Now fast forward, it comes here. Let's say now this data set, these data points will have exact same probability distribution. So probability distribution does not change over time. That is what a strict stationarity means. So that now if I write it in a simple mathematical notation, so basically what I mean by probability of xt1 less than c1, probability of and xt2 less than c2, in this way up to xtk less than ck, this probability distribution or the probability that you will calculate will be exactly same as probability of xt1 plus h less than c1 and probability of xt2 plus h less than c2, in this way xtk plus h less than ck. Now h, k equal to 1, 2, 3, t1, t2, tk is the same in the both side of the equation. C1, C2, Ck are same on the both side of the equation, and h's you can take essentially 0, plus minus 1, plus minus 2. So basically you can go forward or backward, doesn't matter. If you shift forward or backward, distribution stays same. Okay, so this is the idea. Now if you take k equal to 1, then probability of xt less than c and xt plus h less than c, these two have the same probability distribution. This is precisely what it means. Previously I was defining it for the k variable, now I'm just doing it for one, for the marginal distribution, effectively marginal distribution. So it means we can say that mu t is same as mu t plus h. Mu t is mean of the distribution at time t, and mean of the distribution at time t plus h, they are same. If they are same, I can say they are constant. They are not function of time. So that means they are not function of time. So that means a random walk process with drift does not exhibit strict stationarity, because today it could be here, and then if you have a drift, it will be here. So mean will definitely drift. Mean will drift. So a random walk process with a drift is not a stationary process. For sure. Without drift, we will discuss. I am not saying what. But from this very basic definition of stationarity, we can say that random walk process with drift is not stationary, because it is drifting. So that means your expectation at time point t is a mu t, and your expectation at time point t plus h is mu times t plus h. So your means are different, so they are not stationary. Now let's go for k equal to 2. If you take k equal to 2, then and you still have a strict stationarity, then what you will have, xt1 less than c1 and xt2 less than c2, that probability will be exactly same as xt1 plus h less than c1 and xt2 plus h less than c2. It's a bivariate distribution, and that these bivariate distribution is exactly same as t and t plus h. So that means this is a bivariate distribution, so it has its own covariance. If it has its own covariance, then this covariance, and if these two distribution is same at t and t plus h, then covariance at t and covariance at t plus h, they are exactly same. Now you can, we have discussed what is autocovariance, right? So you can take xt at time point t and xt2 at the time point s, so lag variable, then this autocovariance at time point s and t is same as autocovariance at s plus h and t plus h. So autocovariance function of the series xt, that means, is only function of h, because, and they will not be affected by s and t. So you can say that autocovariance function is solely dependent on the time difference of s and t and not s and t itself. So you can write it as a covariance of st is same as covariance of s plus h comma t plus h. From here we can say that autocovariance will be only function of H. Because if you have covariance function at S and T is something like this, right? And S plus H and T plus H is also something like that. Same thing, they have the exact same covariance. Now, if you technically their structure is same. Now, obviously, if they are close, their covariance, you would expect a stronger covariance. If they are different, then you will expect a weaker covariance. So it will be function of H, not, and it will be free from, so, okay, let me just forget about xt1, xt2 and all these things. Just take xt and lag of xt t minus 1. Okay. So now you take t equal to 2, then what you are looking at? You are looking at covariance of xt2 and x2 and x1, right? This covariance, and if you look at the x10 and x9, they will be same by the very definition. If you take S equal to 2 and 1, then that will be exactly same as x 10 and 9. So that's perfectly fine. Now what is the, it will be, but now you take S x1 and x3, you understand, x1 and x3 and x7 and x10, sorry, x7 and x9. If you are taking x1 and x3, that covariance and x1 and sorry x7 and x9, that covariance is also exactly same by this definition, this structural definition of strict stationarity. But do you really think the autocovariance of x1 and x2 and x1 and x3 will be same? They will be different. So that means autocovariance is only function of its lag. If stationarity is there, it will be only function of lag, and it will not depend on at what time point it is standing. You should not expect covariance is different at x13 and x79. They will be same. But what is different is the lag. The covariance between x1 and x2 and covariance between x1 and x5 will be different. So the only difference in the strict stationarity, only difference that you will notice is the covariance because of the lag effect and not because of the time. Because over time my distribution is constant. My distribution is not moving around. Okay. Now if autocovariance is only depending on the time difference or the lag of age, then we can say autocorrelation also function of the lag. Okay. By the way, the concept is clear for you guys? Any doubt? Anybody have any doubt? I'll be happy to repeat that. All right. Same concept. It's just correlation is nothing but you divide that by the variance of by variance of the two variable, square root of the product of two variables. So it's normalized. It gets normalized. But the problem is with the strict stationarity that it is very difficult to assess strict stationarity from a single data set. If you have only single data set, you cannot really assess the stationarity or strict stationarity. So we will move on to a milder version of the stationarity called weak stationarity, which we can assess from the data set. For single data set, we can assess whether the data, the observed value, observed time series is stationary or not. So what is the idea of weak stationarity? In the strict stationarity, what we are saying, we are defining the stationarity in terms of its distribution. We are calling it the entire distribution is same irrespective of the time points. You move on, backward, forward, your distribution is same, which is very strong assumption. In the weak stationarity, what we are doing that you impose the condition based on the moments, first 2 moments or 3 moments. Instead of saying that my distribution is exactly same at time point t and time point t plus 8, we will say, okay, my moments are same as at t and t plus h. Now what does it mean? It means I am allowing the distribution to be normal at time point t and maybe gamma at time t plus h. I am okay with that as long as their moments are exactly same. That means their mean is constant at the same place, their variances are constant, their autocovariances are constant. So autocovariance is only function of lag. If these properties holds good, I am okay with that. This is the idea. All right. So a weak stationary time series xt is a finite variance process such that mu t equal to mu is constant and finite. The covariance function gamma st is gamma of lag mod s minus t is a function of mod s minus t. So now onwards in the entire course, whenever we say stationarity, by default we mean weak stationarity. Okay, so because this is only something we will be able to assess from the data. Strict stationarity we will not be able to assess from the data. So unless mention it is strict stationarity, anytime we mention stationarity, by default you should assume it is weak stationary series. Okay. So that's what I am saying here. So we will use the term stationary to mean weak stationary. Exact. And if a stationary process is stationary in the strict sense, we will use the term strict stationary in that time. Okay. Yeah. See, if it is strict stationary, then these will hold in any way. Yeah, but it doesn't mean that if it holds, that does not mean that the distribution for are same at t and t plus h. So if these two condition holds, that does not mean that distribution is same at t and t plus h. Okay. Some more properties. A strict stationary time series with finite variance is also weak stationary. You will see what is it means. Converse is not true unless there are further conditions. One important case where the stationary implies strict stationarity is if the time series is Gaussian. If you are assuming the entire series is Gaussian, then strict stationarity implies. But that is most of the time you will not see a series which is Gaussian, which is rarely you will see series which is Gaussian. So the mean function expectation of xt is equal to mu t of a stationary time series is independent of t, because my mu t and mu t plus h is same, so we will always write mu t equal to mu. Whenever we will say, oh, you have a stationary time series, by default mode you should mean that it is a weak stationary, and you can take mu t equal to mu. You don't have to worry about that. All right. Now, covariance function is a stationary time series function of s minus t, mod of s minus t. Now, if you take which is essentially gamma t, if you take s equal to t plus h, then gamma t plus h comma t, so which is basically gamma of mod h, only the autocovariance function of lag. And if you take h equal to 0, lag 0, the autocovariance function will give you nothing but the variance of xt. And whenever we will say that it's a stationary time series, along with assuming that it's a weak stationary and its mean is constant, you can also at a default mode you can go and assume that this is a constant, this is also constant. When I'm saying gamma 0 variance of xt is less than infinity, is basically I'm trying to say it is constant, it's some finite value which is free from t, because it's a function of effectively autocovariance which is free from t, so it is a constant. So variance of xt is constant. So mean and variance is constant, and autocovariance is only function of lag, and it is not function of t, the time index. Okay, before we jump on to the next issues, any clear this thing? Okay, let's move on. Autocovariance function of a stationary time series, we can write it as gamma h equal to expectation of x t plus h minus mu times xt minus mu. Now remember that when we first defined it, we write it as a mu t, but now it is stationary, so I am replacing mu t by mu, because I am saying at the beginning that it is stationary time series. Now that means autocorrelation function, you can define it as gamma t plus h square root of gamma t plus h comma t plus h and gamma t comma t. Instead of s, I am taking t plus h. Okay, so that means here I am effectively getting gamma 0, and effectively I am here getting gamma 0. So it is gamma 0, and gamma t plus h comma t is nothing but gamma h. So basically autocovariance of lag h divided by variance of the series, that gives you autocorrelation function as a function of h or function of lag. Clear? Simple. You just now all you have to do, just calculate the autocovariance function of lag and then divide that by the variance of the at lag 0, and you are done, or variance of the time series. that will give you the autocorrelation function over h, over lag. Now you can prove that this guy is always stay between -1 and 1 using Cauchy-Schwarz inequality. The way you prove simple correlation always stays between -1 and 1 using Cauchy-Schwarz inequality. Okay, so that's not a big deal. Now let's take some example to understand what these things in terms of handling data. So let's take the old Nile data. If I plot autocorrelation function of the Nile data, what it tells you, let me explain you. So on the x-axis I am plotting the lags, the h values. From 0 to up to 50 I have taken. At 0 autocorrelation function value is 1, obviously, because if you take h equal to 0, gamma 0 by gamma 0, 1. So it will be 1. At gamma 0 you have a 1. Now h equal to 1 you have near 0.5. Autocorrelation function is near 0.5. At 2 it is slightly below 0.4. Then 3 it's slightly near 0.3, then 0.2, and this way it is constantly reducing. So as h increasing, autocorrelation means the series correlation with itself with the increasing lag is reducing. So we can say that. So that means the xt and xt plus 1 you can expect correlated. So if you have x1 and x2, or if you have x9 and x10, they tend to behave in a similar fashion. They tend to be correlated. But as the value increases, as the lag increases, the correlation is going down, we can say that, all right, x1 and x10, they seems like not correlated, or x10 and x20, the correlation would not be very strong. So now you can see there are two dash blue line, right? That is confidence interval for correlation around 0. Okay, so basically any correlation value which stays between these two bands, you can say effectively their correlation is 0. You can consider as a testing of hypothesis, your null is correlation equal to 0 versus correlation not 0, and if the values stay within these two bands, you can say they are not significant. And if it is outside the band, like first 1, 2, 3, 4, up to 5, 6, 7, 8, up to 8, we see that all these values are outside the band, 95% confidence interval. We can say these first 8 lag values seems to be somewhat correlated with the series itself, and beyond that we don't see much strong correlation. Maybe somewhere at 11, 12, I don't know why, maybe a decadal effect or something is happening, but at this moment we can definitely say that up to 5, 6 lag the correlation is significant. Beyond that, correlation is weak. Now you can ask me, how do you calculate this confidence interval or all these things? It is being discussed in the book. Given the time constraint, I will explain you at least the how, from where the formula is coming. I will not discuss the entire derivation of the formula and all this. That's not even possible within the 4-month framework of the semester, but I will point you out that how it is coming, and I will point you in the book where it is being discussed to a great length. Okay. Now we will discuss what does correlation stationary means. Now consider air passenger data set, the simplest data set we have handled in many times. We have seen this many times. So this is the time, first column is time 1949, January is marked as 0.000, and then February is 1 out of 12, which is 0.083, March is 2 out of 12, which is 0.167. So that's how time index being indexed. Then these are the y values, and these are your lag y values, first lag 1 y values. Now if you plot them, what you see? So on the x axis I am plotting lag values, on the y axis I am plotting the in the x axis I am plotting the lag y, lag 1 y, and on the y axis I am plotting the y values. So they clearly you see they are quite strongly correlated, almost on a line. But what I'm trying to say, this is the initial part of the data set. These are centering around 200, and the later part of the data set, which is centering around maybe 450 or 400. So there is a mean shift in the data set. There is a mean shift. If there is a mean shift, so that means mean is not constant, so data is not constant. So that means my time series is not constant. If the mean shift is happening, that means data is, or the time series is not stationary for sure, because its mean is shifting. If it is not stationary, mean stationary, that who cares? Correlation is also not stationary. And we can see the correlation structure is also looks like much weaker here and much more tighter here. It could be a scaling effect, we don't know at this moment. So what I have tried here, I have taken the 1 to n by 2, and what is the covariance of the first part of the data, what is the correlation at the first part of the data, and then n by 2 plus 1 to n, and what is the covariance of the, so clearly covariance is different as we shift, and correlation is slightly less, 0.91 and here 0.87. So your question is the data stationary just because of the mean shift, and looking at the covariance is different? You can say it's not. Now what I did, so this comes under the sort of exploratory data analysis, EDA kind of thing. I calculated the correlation, moving correlation. Like you can calculate moving average, right? You can calculate moving correlation. You can take this data set, you can take say 1 to 5 and calculate the correlation, and then you move the window by 1 down, from 2 to 6, then 3 to 7, then 4 to 8. In this way you can keep moving the windows and keep calculating the correlation. That is called moving correlation. Okay, and plot that moving correlation. It gives you an interesting feature. Its correlation has its own seasonality. It looks like correlation has its own seasonality. Then I looked into the EU stock market data. Okay, it's an old data set from 1992 to 1998. It's an old data set, but you can take any of these Nifty 50 data from Yahoo Finance or TCS data or Reliance data. from from Yahoo Finance or Apple or IBM, anything you take, and you can replicate the same thing. So I just took it, the older data, and then what I have done, I have taken that US stock market data had 4 indices. One is the called DAX. DAX is the, like for Indian stock market we have the Nifty 50, right? Similarly for German stock market they have DAX. I think DAX 30 or DAX 50, something like that. In that DAX, first thing I have done something called return. I have calculated the return, which is nothing but the consecutive difference of the values. Now, does DAX return looks like stationary to you? At least mean stationary, right? Because if you take, say, between 1992 and 1993, what is the mean of these values? It should be nearly 0. Then you take 94 to 95, what is the mean of the values? Somewhere here it is all hovering around 0, these values. So I plot the time series on the time on the x-axis and value in the y-axis. Similarly, you take 1997 here in this range, what we are seeing? The values are hovering around 0. So the return value of the stock market turns out to be always mean stationary. Means its means tend to hover around 0. Do you think it is variance also stationary? No. Bhumika is saying no. Why? No. Yeah, if you look into this area, you see the volatility of the data set is much lower, or the variability is much lower. Now you go shift here, variability of the data set is much higher. So the data set is interesting. It's a mean stationary process, but the variance may not be stationary. Actually, it is not stationary. We know now stock market data is never variance stationary. Variance changes over time. But if you don't know that fact, suppose you don't know, you are new in the stock market, just looking at the DAX return of the time series, which is nothing but consecutive differences, immediately you can figure it out. It's a mean stationary, but variance is not necessarily same over the time. We have not even looked into the autocovariance, correlation, and all these things. That we will do later. But just looking at the simple plot, you can say that variance is not stationary, because there are places like here, where the variability is much less. Here variability is much less, and then sudden boom here, then quite reasonable high variability here. Okay. So the variability fluctuates over time. So variance fluctuates over time. So here I have taken the consecutive differences, the return data and the lag of the return data. I'll show you how to do all those things. And then here is the moving correlation for lag 1. I have calculated. Now the moving correlation for lag 1 is, you can see that for lag 1 looks like it is quite sticky. It's not like completely jittery, sort of a completely white noise. It's not, definitely not white noise. There's some information and some homework. If the white noise is stationary in time series, find autocovariance function. I have already assigned this, right, guys, or not? Yeah. All right. Now what is the idea of joint stationarity? So you have, so far we are only handling single time series, right? Now, not necessarily this will be single time series. It could be multiple time series, like X, Y, Z. Like you remember we had a air pollution data set where we have ozone data, then other pollutions, radiation data, solar radiation, temperature, right? So similarly, you have two time series. Xt is one time series and Yt a time series, and they are jointly stationary. Their joint distribution is stationary. What does it mean? That means effectively they are each stationary. First of all, they has to be joined. When they are saying, we are saying that Xt and Yt are jointly stationary. First of all, Xt and Yt themselves should be stationary, right? Like their mean variance should be constant, both mean Xt and Yt, and their autocovariance functions also only function of their lag. Then it comes their joint cross covariance function. What is cross covariance function? Now, I take Xt plus H minus mu X and Yt minus mu Y. Now, why I am saying mu X and not T? Because they are stationary. I already said they are joint stationary, so they themselves must be stationary. But here mean of not, because now I have two series, I have to mention which mean it is. I cannot take mu Y here. So the mean of the X series and mean of the Y series. In the previous, I can take only mu because it's a same series. So the mean for the series will be the same. If it is a stationary, I don't care that much. Clear? And it is function of only lag H. So the cross covariance is only function of lag H and nothing else. Now you can define cross correlation function, which is effectively autocovariance, or sorry, not autocovariance, this is the cross covariance of xy over H divided by square root of variance of X and variance of H times variance of H. So gamma x0 will give you the variance of X series and gamma y0 will give you the variance of Y series. So you multiply them, take the square root, effectively standard deviation of X and standard deviation of Y. And on the top you have the covariance of X and Y, not exactly the series but the lag H. Okay. And this cross correlation will be again between -1 and 1 because of the same Cauchy-Schwarz inequality will kick in. Now, cross correlation functions generally satisfy this rho x y h equal to rho yx minus h. So instead of xy, if you take yx, so naturally your lag will be, instead of h, it will be minus h. If you just swap, so it will be symmetry in that sense. Let us do an exercise of joint stationarity. Suppose Wt and Wt minus 1 are white noise. Now, from these two white noise, or this white noise itself, I define two series, xt and yt. Xt is Wt plus Wt minus 1, and yt is the wt minus 1. Wt are mean independent random variable with mean 0 variance sigma square, sigma w square. Now these are the things you have to show. Gamma x0 equal to gamma y0 equal to 2 sigma w square. Gamma x1 equal to gamma x minus 1 is sigma w square. Gamma y1 equal to gamma y minus 1. I think it should be just sigma w square. I just made a mistake. I have to just check. Gamma xy1 is sigma w square. Gamma xy is 0. The covariance is 0. And then gamma xy minus 1 is minus sigma w square. And the most interesting part is this result. Other results are to an extent shows that one thing, that after this operation there some covariance are not 0. After these operations they're different. I mean they're definitely autocovariance are different. Now this result shows an interesting feature. H equal to 0 is at 0, h equal to 1 is half, the autocorrelation is half, and h equal to minus 1 it is minus half, and greater than 2 it is 0. Now that means at lag 1 x and y have some correlation. Essentially that is what it means. At lag 0 they don't have a correlation. Lag more than 2 or more than 2 they don't have a correlation, but at exactly lag 1 they have a correlation of half or minus half depending on plus h or minus h. Okay, so that means they're and this is cross correlation. So even if this was an interesting thing, that even if their W are it themselves are white noise, but after this operation, after this simple linear transformations, nothing of the white noise, you introduced a correlation of lag 1. Now another example where we use prediction using cross correlation. After that we will stop and we will meet in the next lecture. Consider the model, say yt equal to ax t minus 1 plus omega t. Now this holds. The series xt is said to lead to yt, so that means for L greater than 0 and say to lag yt L less than 0. So the first thing, you have expectation of xt and expectation of yt is 0. The noise wt is uncorrelated with xt series. The cross covariance function can be computed as, like, you have to take expectation of yt plus h xt. Now you replace yt plus h by ax t plus h minus L plus omega t. That will give you a is a constant, it comes out of the expectation. So you have expectation of x t plus h minus L xt plus expectation of omega t plus h xt. I have already said that this guy is 0, they are uncorrelated, so this part is 0, and what is this? This part is gamma x h minus L. It is covariance, it will give you the autocovariance of x of a lag h minus L. Okay, so cross covariance in this model, cross covariance function will look like autocovariance of input series xt. So you don't, with a peak on the positive side xt and lead on the yt, and peak negative side xt if xt lacks yt, whatever. Now what does it mean? This small simple cute example shows you that if you can write up, when you as a data scientist you are trying to implement this guy, all you have to do, just write one autocovariance function for the series, and you can, and if you know your model is in this kind of structure, yt equal to a of xt minus 1 or xt minus 2 or whatever plus omega t, you can exploit that structure and you can just use the autocovariance function to compute the cross correlation function or cross covariance function. You understand what I mean? In this way you can reduce your computational burden and make your entire process faster. Okay, so there are a lot of tricks. You can do these small problems. You will see a lot of tricks that you can keep in your under your sleeves, and whenever you need to implement something related to your time series data, you can use these tricks and make your implementation much more runtime efficient. These kind of operations, if you can, so for example, if you go there, I can write this as a x, y as a sort of a w kind of thing. You can write x and y, a and w, because all you a is 1, 1, 1 minus 1, and omega t minus 1. Whenever you have a linear transformations, try to write it in a matrix notation. When you will do some business optimization, suppose you are doing a business optimization, most of the time business optimization, the restrictions comes in a linear operations. Okay? Write down your all business restrictions from your optimization in a simple, if you can write it down in this kind of format, it could be like, there could be 5 variables, but they are only doing some plus and minus and multiplication. Then you can, and you have a 3 equation or 4 equation, so it will depend on how many business restrictions you are handling, maybe sometimes hundreds of restrictions, fine. Put all of them in a, all these linear restrictions, majority of the time these business rules are linear operations, into some kind of this a times x kind of format. And then once you can write it, put it into the x times x kind of format, instead of evaluating each business restriction as a single line operation, you do it as a matrix operation. It will be much faster. So whenever as a data scientist you will be working, think in, not only understand the theory part of it, you also think from a runtime efficiency part of it. You also have to think in that part of it. Okay, so I'll stop here and let's meet at the 2 o'clock. Okay guys, thank you very much.